Diploma in Electrical Engineering. Switchgear and Protection System. NoteWise Academy. Let's start. Smiling face heart heart.
Unit 4. Relays and Instrument Transformers. Answer. Relays and instrument transformers are essential components in electrical systems for various purposes. Here's an overview of each. Relays. Construction. Relays typically consist of a coil, an armature, contacts, and an enclosure. When the coil is energized, it generates a magnetic field that attracts the armature, causing the contacts to close or open, depending on the relay type. Types. There are various types of relays, including electromagnetic relays, solid-state relays, thermal relays, and differential relays, each designed for specific applications and operating principles. Function. Relays are used to control electrical circuits by opening or closing contacts in response to electrical or non-electrical input signals. They provide functions such as protection, monitoring, sequencing, and interlocking in electrical systems. Applications. Relays are widely used in industrial automation, power generation and distribution, motor control, safety systems, telecommunications, and automotive electronics. Instrument transformers. Construction. Instrument transformers include current transformers, CTs, and voltage transformers, VTs. They typically consist of a primary winding, a secondary winding, and a magnetic core. CTs have a primary winding connected to the circuit carrying the current to be measured, while VTs have a primary winding connected to the circuit voltage. Function. Instrument transformers are used to step down high currents or voltages to levels suitable for measurement or protection purposes. CTs provide reduced current outputs proportional to the primary current, while VTs provide reduced voltage outputs proportional to the primary voltage. Accuracy. Instrument transformers are designed to provide accurate and precise measurements of current and voltage in electrical systems. The accuracy of the measurements depends on factors such as the transformer design, the quality of the materials used, and the calibration process. Applications. Instrument transformers are used in conjunction with instruments such as ammeters, voltmeters, wattmeters, energy meters, and protective relays to monitor and control electrical parameters in power systems, substations, industrial plants, and commercial buildings. Overall, relays and instrument transformers play crucial roles in ensuring the safety, reliability, and efficiency of electrical systems by providing control, measurement, and protection functions. They are integral components in various applications across different industries and sectors. 4.1. Operating Principle. Answer. The operating principle of relays and instrument transformers is fundamental to understanding their functionality in electrical systems. Here's an overview of the operating principles of each. Relays. 1. Electromechanical relays. Principle. Electromechanical relays operate on the principle of electromagnetic induction. When an electrical current flows through the coil solenoid of the relay, it creates a magnetic field that attracts or repels a movable armature. Operation. The movement of the armature either opens or closes one or more sets of contacts, completing or interrupting the electrical circuit. This action is analogous to manually operating a switch but is controlled by the flow of electrical current through the relay coil. Types. Electromechanical relays come in various types, including normally open NO, normally closed NC, latching, time delay, and protective relays. 2. Solid-state relays, SSRs. Principle. Solid-state relays use semiconductor devices, such as thyristors, SCRs, triacs, or MOSFETs, to perform switching without any moving parts. Operation. When an input signal is applied to the control circuit of the SSR, the semiconductor device is triggered into conduction, allowing current to flow through the output circuit. When the input signal is removed, the semiconductor device turns off, interrupting the current flow. Advantages. SSRs offer faster switching speeds, higher reliability, and longer operational life compared to electromechanical relays. They are also more resistant to vibration and shock and generate less electromagnetic interference. Instrument transformers. 1. Current transformers, CTs. Principle. Current transformers operate on the principle of electromagnetic induction. A primary winding, connected in series with the current-carrying conductor to be measured, induces a proportional current in a secondary winding. Operation. The secondary current is a scaled-down replica of the primary current and is proportional to it. This secondary current is then used for measurement, protection, or control purposes. Accuracy. CTs are designed to provide accurate current measurements under normal operating conditions and maintain a specified accuracy class over a range of primary current levels. 2. Voltage transformers, VTs, or potential transformers, PTs. Principle. Voltage transformers also operate on the principle of electromagnetic induction. A primary winding is connected in parallel with the circuit or equipment whose voltage is to be measured, while the secondary winding is connected to the measuring or protective devices. Operation. The secondary voltage is a scaled-down replica of the primary voltage and is proportional to it. VTs provide accurate voltage measurements for metering, protection, and control purposes. Accuracy. VTs are designed to provide precise voltage transformation and maintain a specified accuracy class over a range of primary voltage levels. In summary, relays operate by using electromagnetic principles to control the flow of electrical current in circuits, while instrument transformers utilize electromagnetic induction to measure and monitor electrical parameters such as current and voltage in power systems. Both play critical roles in ensuring the safety, protection, and efficiency of electrical installations. 4.2. Relay characteristics. Answer. The characteristics of relays vary depending on their type, design, and intended application. Here are some key characteristics commonly associated with relays. 1. Contact arrangement. Relays can have different contact arrangements, including normally open NO, normally closed NC, or changeover CO contacts. The contact arrangement determines the default state of the contacts when the relay is not energized and whether the contacts switch from one state to another when the relay is energized. 2. Coil voltage and current. Relays have a specified coil voltage and current rating, which determine the electrical parameters required to energize the relay coil. It's essential to match the coil voltage and current requirements of the relay with the voltage and current available in the control circuit. 3. Contact rating. The contact rating of a relay indicates the maximum voltage and current that the contacts can safely handle when switching a load. It's crucial to select a relay with contact ratings that are compatible with the electrical load being switched to prevent damage to the relay contacts and ensure reliable operation. 4. Response time. Response time refers to the time it takes for the relay contacts to change state after the coil is energized or de-energized. Faster response times are desirable in applications where rapid switching is required, such as in protective relays for fault detection and mitigation. 5. Operating temperature range. Relays are designed to operate within a specified temperature range, which ensures their performance and reliability under various environmental conditions. It's essential to select relays with operating temperature ranges that match the ambient temperature conditions of the installation environment. 6. Mechanical life and electrical life. The mechanical life of a relay refers to the number of mechanical operations, opening and closing of contacts that the relay can withstand before failure. The electrical life of a relay refers to the number of electrical operations, energizing and de-energizing of the coil that the relay can withstand before failure. 7. Mounting style. Relays come in various mounting styles, including PCB mount, socket mount, panel mount, and DIN rail mount, to accommodate different installation requirements. The mounting style of the relay should be compatible with the mounting options available in the application. 8. Special features. Some relays come with special features such as LED indicators, test buttons, built-in diodes for suppression of back EMF, and transient voltage protection. These features enhance the functionality and usability of the relay in specific applications. In summary, the characteristics of relays play a significant role in determining their suitability for a particular application. It's essential to consider these characteristics carefully when selecting relays to ensure reliable operation and optimal performance in the intended application. 4.2.1. Instantaneous relays. Answer. Instantaneous relays, also known as instantaneous overcurrent relays, are a type of protective relay commonly used in electrical power systems to detect and quickly respond to fault conditions. Here are the key characteristics of instantaneous relays. 2. Threshold setting. Instantaneous relays are typically set to trip when the current flowing through the protected circuit exceeds a specified magnitude. This threshold is set based on the maximum allowable current for the circuit and the desired level of protection. 3. Fixed setting. Instantaneous relays have a fixed trip setting, meaning that once the threshold is set, it remains constant and does not change over time or with variations in load conditions. This fixed setting provides rapid and consistent protection against overcurrent faults without the need for adjustment. 4. High-speed operation. Instantaneous relays operate with high speed, tripping the circuit breaker within milliseconds of detecting an overcurrent fault. This high-speed operation helps prevent damage to equipment and minimizes downtime by quickly isolating the faulted section of the electrical system. 5. Application. Instantaneous relays are commonly used in distribution systems, transmission lines, motors, generators, transformers, and other critical equipment to provide primary protection against overcurrent faults. They are particularly effective in protecting against short circuits and other severe fault conditions that require immediate action to prevent damage and ensure system stability. 6. Coordination with other protective devices. Instantaneous relays are often coordinated with other protective devices, such as time-delayed relays and backup relays, to provide comprehensive protection and coordination within the electrical system. Proper coordination ensures that the instantaneous relay operates only for faults within its protected zone while allowing downstream protective devices to clear faults in their respective zones. In summary, instantaneous relays play a crucial role in providing fast and reliable protection against overcurrent faults in electrical power systems. Their high-speed operation and fixed trip setting make them well suited for protecting critical equipment and ensuring the safety and reliability of the electrical infrastructure. 4.2.2. Inverse relays. Answer. Inverse relays, also known as inverse time overcurrent relays, are a type of protective relay commonly used in electrical power systems to detect and respond to overcurrent conditions. Here are the key characteristics of inverse relays. 1. Operation principle. Inverse relays operate based on the principle of inverse time overcurrent protection. They are designed to trip circuit breakers or other protective devices when the current flowing through the protected circuit exceeds a predetermined threshold for a specified period. The trip time of the relay is inversely proportional to the magnitude of the overcurrent. Higher currents result in faster trip times, while lower currents result in longer trip times. 2. Inverse time characteristic. The time-current characteristic curve of an inverse relay is nonlinear and exhibits an inverse relationship between the current magnitude and the trip time. At low current levels, the trip time is longer, allowing the system to tolerate temporary overloads and inrush currents without unnecessary tripping. As the current magnitude increases, the trip time decreases, providing faster protection against more severe overcurrent faults, such as short circuits. 3. Settings adjustment. Inverse relays allow for adjustment of the current pickup setting and the time delay settings to accommodate different system requirements and protection objectives. The pickup setting determines the current threshold at which the relay starts to operate, while the time delay settings control the trip time characteristics of the relay. 4. Adaptive characteristics. Some modern inverse relays feature adaptive or programmable characteristics that allow for fine-tuning of the trip time response based on the specific characteristics of the protected equipment and the operating conditions of the system. Adaptive relays can automatically adjust their trip characteristics in real time to optimize protection and coordination within the electrical system. 5. Application. Inverse relays are commonly used in distribution systems, transmission lines, motors, transformers, and other critical equipment to provide primary protection against overcurrent faults. They are particularly effective in protecting against sustained overloads and faults with varying current magnitudes, providing both selective coordination and reliable fault clearance. 6. Coordination with other protective devices. Inverse relays are typically coordinated with other protective devices, such as instantaneous relays and backup relays, to provide comprehensive protection and coordination within the electrical system. Proper coordination ensures that the relay operates selectively and discriminately, clearing faults in its protected zone while allowing downstream protective devices to respond to faults in their respective zones. In summary, inverse relays provide adaptive and selective protection against overcurrent faults by adjusting their trip characteristics. 4.2.3. IDMT relays. Answer. Inverse definite minimum time (IDMT) relays are a type of protective relay commonly used in electrical power systems to provide overcurrent protection. Here are the key characteristics of IDMT relays. 1. Operation principle. IDMT relays operate based on the principle of inverse time overcurrent protection. They are designed to trip circuit breakers or other protective devices when the current flowing through the protected circuit exceeds a predetermined threshold for a specified period. The trip time of the relay is inversely proportional to the magnitude of the overcurrent. Higher currents result in faster trip times, while lower currents result in longer trip times. However, unlike standard inverse relays, IDMT relays have a definite minimum time delay to prevent unnecessary tripping for very high currents. 2. Characteristic curve. The trip time of an IDMT relay is determined by its characteristic curve, which is typically represented on a logarithmic scale. The curve exhibits an inverse relationship between the current magnitude and the trip time. At low current levels, the trip time is longer, allowing the system to tolerate temporary overloads and inrush currents without unnecessary tripping. As the current magnitude increases, the trip time decreases according to the inverse characteristic curve. 3. Settings adjustment. IDMT relays allow for adjustment of several parameters, including the current pickup setting, the time multiplier setting, also known as the plug setting multiplier, and the definite time delay. The current pickup setting determines the current threshold at which the relay starts to operate, while the time multiplier setting adjusts the slope of the characteristic curve. The definite time delay setting specifies the minimum time delay for very high overcurrents to prevent nuisance tripping. 4. Application. IDMT relays are widely used in distribution systems, transmission lines, motors, transformers, and other critical equipment to provide primary protection against overcurrent faults. They are particularly effective in protecting against sustained overloads, faults with varying current magnitudes, and selective coordination with other protective devices. 5. Coordination with other protective devices. IDMT relays are typically coordinated with other protective devices, such as instantaneous relays and backup relays, to provide comprehensive protection and coordination within the electrical system. Proper coordination ensures that the relay operates selectively and discriminately, clearing faults in its protected zone while allowing downstream protective devices to respond to faults in their respective zones. In summary, IDMT relays offer adaptive and selective protection against overcurrent faults by adjusting their trip characteristics based on the magnitude and duration of the fault current. Their definite minimum time delay feature prevents unnecessary tripping for very high currents, ensuring reliable fault clearance and system stability. 4.2.4. Plug setting and time setting of relays and related numerical. Answer. In the context of IDMT inverse definite minimum time relays, the plug setting and time setting are crucial parameters that determine the operation of the relay. Here's an explanation of each, along with related numerical values. 1. Plug setting. The plug setting of an IDMT relay, also known as the plug setting multiplier, PSM, or current setting multiplier, determines the current threshold at which the relay starts to operate. It is expressed as a ratio or percentage of the rated current, IR, of the protected circuit. The plug setting multiplier, PSM, is typically denoted as K, and it is calculated using the formula K equals frac I underscore pickup I underscore R, where I underscore pickup is the pickup current setting of the relay. The plug setting multiplier is used to adjust the sensitivity of the relay to overcurrents. A higher plug setting results in a more sensitive relay that operates at lower currents, while a lower plug setting makes the relay less sensitive and requires higher currents to operate. 2. Time setting. The time setting of an IDMT relay determines the characteristic operating time of the relay for a given overcurrent magnitude. It is expressed as a time multiplier, TMS, which is a factor applied to the standard time current characteristic curve of the relay. The time setting multiplier, TMS, is denoted as T, and is typically set based on the desired time delay for the relay to operate at a specific multiple of the pickup current. The relationship between the time setting multiplier, TMS, and the characteristic operating time, T, of the relay is given by T equals frac TMS, Fi, where Fi is the characteristic curve function that determines the operating time based on the magnitude of the overcurrent. The time setting multiplier is used to adjust the slope of the characteristic curve, with higher values resulting in faster tripping times for higher overcurrents. Numerical example. Suppose we have an IDMT relay with the following settings. Rated current I underscore R 100A. Pickup current I underscore pickup 50A. Time setting multiplier TMS 0.1 for a time delay of 0.1 seconds at 10 times the pickup current. We can calculate the plug setting multiplier, PSM, as K equals frac I underscore pickup I underscore R equals frac 50 text A 100 text A equals 0.5. And the characteristic operating time T for an overcurrent of 10 times the pickup current 10 times I underscore pickup as T equals frac TMS Fi equals frac 0.1 text S 10 equals 0.01 text S. These values represent the sensitivity and response time of the IDMT relay to overcurrent faults in the protected circuit. Adjusting the plug setting and time setting allows for fine-tuning of the relay's performance to meet specific protection requirements. 4.3. Classification of relays based on construction. Answer. Relays can be classified based on their construction into several categories. Here are some common classifications. 1. Electromechanical relays. Electromechanical relays use a combination of electromagnets and mechanical contacts to operate. They consist of a coil, armature, and one or more sets of contacts. When the coil is energized, it creates a magnetic field that attracts the armature, closing or opening the contacts to control the flow of current in the circuit. 2. Solid-state relays, SSRs. Solid-state relays use semiconductor devices such as thyristors, SCRs, triacs, or MOSFETs to perform switching without any moving parts. They typically consist of an input circuit, an output circuit, and a control circuit. When a control signal is applied to the input circuit, the semiconductor device in the output circuit is triggered into conduction, allowing current to flow through the output circuit. 3. Hybrid relays. Hybrid relays combine the features of electromechanical relays and solid-state relays. They may use electromechanical components for switching high-power loads and solid-state components for control and signal processing. 4. Latching relays. Latching relays maintain their last state, either open or closed, even after the control signal is removed. They typically use a bistable mechanism to lock the contacts in position until a reset signal is applied. 5. Reed relays. Reed relays use a small glass tube containing two flexible metal reeds that act as the contacts. When a magnetic field is applied to the reeds, they are drawn together to make contact, completing the circuit. 6. Polarized relays. Polarized relays use a permanent magnet or a polarized electromagnet to ensure that the contacts operate in a specific direction. They are often used in applications where the polarity of the control signal or the direction of current flow is critical. 7. Bimetallic relays. Bimetallic relays use the differential expansion of two metals with different coefficients of thermal expansion to operate. When the ambient temperature changes, the differential expansion causes a mechanical deformation that actuates the relay contacts. 8. Microelectromechanical systems MEMS relays. MEMS relays use microfabrication techniques to create miniature electromechanical relays on a silicon substrate. They offer advantages such as small size, low power consumption, and high reliability for use in microelectronic applications. These classifications provide a broad overview of the types of relays available, each with its own advantages, disadvantages, and applications. The choice of relay construction depends on factors such as the specific requirements of the application, cost considerations, and environmental conditions. 4.4. Electromagnetic induction relay. Answer. Electromagnetic induction relays are a type of protective relay that operate based on the principle of electromagnetic induction. They are commonly used in electrical power systems to detect abnormal conditions such as overcurrents, undercurrents, or faults and initiate appropriate actions to protect the system. Here are the key features and characteristics of electromagnetic induction relays. 1. Operation principle. Electromagnetic induction relays operate on the principle of electromagnetic induction, which states that a changing magnetic field induces a voltage or current in a nearby conductor. When the current in the circuit being monitored exceeds a predetermined threshold, it generates a magnetic field around the conductor. This changing magnetic field induces a current in a sensing coil or winding of the relay, proportional to the current in the protected circuit. The induced current in the sensing coil actuates the relay mechanism, causing it to trip or operate based on the relay's configuration. 2. Construction. Electromagnetic induction relays typically consist of a sensing coil, a movable armature, and one or more sets of contacts. The sensing coil is connected in series with the circuit being monitored, and the induced current in the coil is proportional to the current in the protected circuit. The induced current creates a magnetic field that attracts or repels the armature, depending on the relay's design and configuration. The movement of the armature actuates the contacts, either opening or closing the circuit to initiate the desired protective action. 3. Characteristics. Electromagnetic induction relays can be configured with different characteristics, including inverse time, definite time, or instantaneous tripping. The characteristic curve of the relay determines the relationship between the current magnitude and the operating time of the relay. Inverse time relays exhibit longer operating times for lower currents and shorter operating times for higher currents, providing selective coordination and discrimination for various fault conditions. Definite time relays operate with a fixed time delay for all current levels above the pickup threshold, suitable for applications requiring a constant trip time. Instantaneous relays operate without any time delay, tripping the circuit breaker immediately when the current exceeds a predetermined threshold. 4. Applications. Electromagnetic induction relays are widely used for overcurrent protection in distribution systems, transmission lines, motors, generators, transformers, and other critical equipment. They provide primary protection against faults such as short circuits, overloads, and ground faults, helping to prevent damage to equipment and ensure the safety and reliability of the electrical system. In summary, electromagnetic induction relays are essential components of protective relay systems in electrical power systems. They operate based on the principle of electromagnetic induction, detecting abnormal conditions in the protected circuit and initiating appropriate protective actions to prevent damage and ensure the reliable operation of the system. 4.5. Characteristics of directional relay. Answer. Directional relays are a type of protective relay used in electrical power systems to detect faults and abnormalities in the system and selectively trip circuit breakers to isolate the faulted section. Here are the key characteristics of directional relays. 1. Directional sensing. The primary characteristic of directional relays is their ability to determine the direction of fault currents flowing in the system. Directional relays are equipped with directional elements or algorithms that analyze the phasor relationships of currents and voltages to determine the direction of fault currents. By distinguishing between forward and reverse fault currents, directional relays can selectively trip the circuit breaker closest to the fault, minimizing the impact on the rest of the system. 2. Operating principle. Directional relays operate based on the principle of comparing the phase angles of current and voltage signals to determine the direction of power flow. When a fault occurs, the current flowing through the relay's sensing elements is compared with the voltage phasor to determine whether the fault is in the forward or reverse direction relative to the relay's location. If the fault is in the forward direction, the relay initiates a trip signal to isolate the faulted section of the system. If the fault is in the reverse direction, the relay remains inoperative to prevent unnecessary tripping. 3. Characteristics. Directional relays can be characterized by several parameters, including sensitivity, selectivity, stability, and speed of operation. Sensitivity refers to the ability of the relay to detect fault currents accurately, even at low levels, while selectivity ensures that the relay operates only for faults within its protected zone.
Stability refers to the ability of the relay to remain stable and immune to false tripping due to transient conditions or external disturbances. Speed of operation determines how quickly the relay responds to fault conditions to isolate the faulted section and prevent damage to equipment. 4. Modes of operation. Directional relays can operate in various modes, including forward, reverse, or bidirectional sensing modes, depending on the specific requirements of the application. In forward sensing mode, the relay trips for faults occurring in the forward direction relative to its location. In reverse sensing mode, the relay trips for faults occurring in the reverse direction relative to its location. In bidirectional sensing mode, the relay can trip for faults occurring in either the forward or reverse direction, providing flexibility in protection schemes. 5. Applications. Directional relays are commonly used in transmission lines, distribution feeders, busbars, and interconnections between power systems. They provide selective protection against faults, allowing for rapid isolation of faulted sections and minimizing the impact on the rest of the system. Directional relays are essential for maintaining system stability, reliability, and continuity of service in electrical power systems. In summary, directional relays play a crucial role in providing selective protection and ensuring the reliable operation of electrical power systems. They detect fault currents and determine their direction to initiate appropriate protective actions, helping to prevent damage to equipment and maintain system stability. 4.6. Introduction to static and digital relay. Answer. Static relays and digital relays are modern types of protective relays that offer several advantages over traditional electromechanical relays. Here's an introduction to each. Static relays. Static relays, also known as solid-state relays, use electronic components such as transistors, diodes, and integrated circuits to perform the relay function without any moving parts. They rely on electronic circuits and devices to detect abnormal conditions in the electrical system and initiate protective actions. Here are some key points about static relays. 1. Operation. Static relays operate based on electronic circuits and devices, which provide fast and accurate detection of fault conditions. 2. Advantages. Faster operation. Static relays have faster response times compared to electromechanical relays, making them more suitable for high-speed protection applications. Higher reliability. Solid-state components have longer lifespans and are less susceptible to wear and tear than mechanical components, resulting in increased reliability. Lower maintenance. Static relays require less maintenance compared to electromechanical relays since they have no moving parts to wear out or become misaligned. Enhanced flexibility. Solid-state components allow for more flexibility in relay design and functionality, enabling advanced protection features and customization options. 3. Applications. Static relays are used in a wide range of applications, including motor protection, generator protection, transformer protection, feeder protection, and busbar protection. They are particularly well suited for applications requiring high-speed, precise, and reliable protection, such as in industrial and utility power systems. Digital relays. Digital relays, also known as numerical relays or microprocessor-based relays, use digital signal processing (DSP) technology to perform protection functions. They convert analog signals from current and voltage transformers into digital signals, allowing for advanced processing and analysis. Here are some key points about digital relays. 1. Operation. Digital relays use microprocessors and software algorithms to detect abnormal conditions, analyze fault characteristics, and initiate protective actions. 2. Advantages. Advanced protection features. Digital relays offer advanced protection features such as adaptive protection, communication capabilities, self-monitoring, and diagnostics. Programmability. Digital relays are highly programmable, allowing for easy configuration and customization of protection settings, logic, and communication protocols. Data logging and communication. Digital relays can store and transmit data related to fault events, operating conditions, and system performance, facilitating remote monitoring, analysis, and control. Compatibility with modern systems. Digital relays are compatible with modern communication protocols such as IEC 61850, enabling seamless integration into supervisory control and data acquisition (SCADA) systems and substation automation schemes. 3. Applications. Digital relays are widely used in substations, power plants, industrial facilities, and utility grids for protection, control, monitoring, and automation purposes. They provide comprehensive protection against various types of faults and abnormalities, helping to ensure the safety, reliability, and efficiency of electrical power systems. In summary, static relays and digital relays represent advancements in protective relay technology, offering faster operation, higher reliability, enhanced functionality, and greater flexibility compared to traditional electromechanical relays. They play a crucial role in ensuring the protection, control, and monitoring of modern electrical power systems. 4.7. Buchholz relay construction and characteristics. Answer. Buchholz relays are protective devices primarily used in oil-immersed transformers and reactors to detect and respond to incipient faults such as internal arcing or partial discharges. Here's an overview of the construction and characteristics of Buchholz relays. Construction. 1. Main tank connection. Buchholz relays are typically installed in the pipe connecting the main tank of the transformer or reactor with the conservator tank, which contains the oil expansion space. 2. Gas accumulator. The relay consists of a gas accumulator or chamber connected to the main tank. This chamber collects any gases generated within the transformer due to incipient faults. 3. Float mechanism. Inside the gas accumulator, there is a float mechanism consisting of a hinged float connected to a pivot. The float is designed to rise or fall based on the accumulation of gas within the chamber. 4. Contacts. The float mechanism is connected to electrical contacts, typically mounted on a relay base. When the float rises or falls beyond a certain threshold, it actuates the contacts to open or close the relay circuit. 5. Alarm contacts. Buchholz relays often have two sets of contacts, one for alarm and another for tripping. The alarm contacts are used to signal a warning when gas accumulation exceeds a predetermined level, indicating the presence of a potential fault. 6. Trip contacts. The trip contacts are activated when gas accumulation reaches a critical level, indicating the occurrence of a severe fault. These contacts initiate a trip signal to disconnect the transformer from the power system to prevent further damage. Characteristics. 1. Gas sensitivity. Buchholz relays are highly sensitive to the presence of gases generated by internal faults such as arcing, overheating, or insulation breakdown. Even small amounts of gas accumulation can trigger the relay's operation. 2. Response time. Buchholz relays offer rapid response to incipient faults, providing early warning and protection against more severe damage. The relay can detect faults at their initial stages, allowing for timely intervention to prevent catastrophic failures. 3. Adjustability. The sensitivity and response characteristics of Buchholz relays can be adjusted to suit the specific requirements of the transformer or reactor they protect. This allows for customization based on factors such as the size, rating, and operating conditions of the equipment. 4. Reliability. Buchholz relays are known for their reliability and robustness, making them a popular choice for transformer protection. They have a simple and durable design, with few moving parts, minimizing the risk of mechanical failure. 5. Maintenance. Buchholz relays require periodic inspection and maintenance to ensure proper operation. This includes checking for gas accumulation, verifying the integrity of the float mechanism, and testing the relay's contacts and electrical connections. Overall, Buchholz relays play a crucial role in providing early detection and protection against incipient faults in oil-immersed transformers and reactors, helping to maintain the integrity, reliability, and safety of electrical power systems. 4.8. Court and PT. Answer. Current transformers, CTs, and potential transformers, PTs, also known as voltage transformers, VTs, are essential components of power systems used for metering, protection, and control purposes. Here's an overview of CTs and PTs. Current transformers, CTs. 1. Purpose. CTs are used to measure or sense the current flowing in a conductor. They step down the high primary current to a proportional lower secondary current, which is safe for metering, protection, and control devices. 2. Construction. CTs consist of a primary winding, which is connected in series with the power conductor carrying the primary current. The secondary winding is connected to measuring, protection, or control devices. The core material is typically made of laminated steel or a magnetic alloy, and the windings are insulated and enclosed in a housing. 3. Ratio and accuracy. CTs are rated by their nominal ratio, which defines the relationship between the primary and secondary currents. Common ratios include 100/5, 200/5, and 400/5, where the primary current is divided by the secondary current. CTs are designed to operate within specified accuracy classes, such as 0.1, 0.2, 0.5, 1, and 3. These classes indicate the maximum permissible error under rated conditions. 4. Applications. Metering. CTs are used in conjunction with watt-hour meters to measure energy consumption accurately. Protection. CTs provide input signals to protective relays, which monitor the current flow and trip circuit breakers or other protective devices in case of abnormal conditions such as overcurrents or short circuits. Control. CTs help monitor and control the operation of electrical equipment by providing feedback signals to control systems. Potential transformers, PTs. 1. Purpose. PTs are used to step down high system voltages to safe and measurable levels for metering, protection, and control purposes. They provide a low voltage signal proportional to the system voltage. 2. Construction. PTs consist of a primary winding connected across the system voltage and a secondary winding connected to metering, protection, or control devices. Like CTs, PTs have a core made of laminated steel or a magnetic alloy and insulated windings enclosed in a housing. 3. Ratio and accuracy. PTs are also rated by their nominal ratio, which defines the relationship between the primary system voltage and the secondary output voltage. Typical ratios include 120/120, 120/108, and 120/140. PTs are designed to operate within specified accuracy classes, similar to CTs. 4. Applications. Metering. PTs provide scaled-down voltage signals to metering devices for measuring voltage levels in the power system accurately. Protection. PTs supply input signals to protective relays, allowing them to monitor voltage levels and detect abnormalities such as overvoltage or undervoltage conditions. Control. PTs help monitor and control the operation of electrical equipment by providing feedback signals to control systems. In summary, CTs and PTs are essential components of power systems, enabling accurate metering, reliable protection, and effective control of electrical equipment. They play a crucial role in ensuring the safety, reliability, and efficiency of power generation, transmission, and distribution systems. 4.8.1. Application of CT and PT in power system protection. Answer. Current transformers, CTs, and potential transformers, PTs, are vital components in power system protection, providing essential inputs for protective relays to detect abnormal conditions and initiate appropriate actions to safeguard the electrical network. Here are some key applications of CTs and PTs in power system protection. 1. Overcurrent protection. CTs are used to measure the current flowing through power lines and feeders. Protective relays receive the current signals from CTs and compare them to preset thresholds. In the event of an overcurrent condition, the relay issues a trip signal to circuit breakers or other protective devices to isolate the fault. 2. Distance protection. PTs are used to provide voltage signals to protective relays. Distance relays compare the voltage and current phasors to determine the impedance of the transmission line. If the impedance falls outside the preset limits, indicating a fault, the relay initiates a trip signal to isolate the faulted section of the line. 3. Differential protection. CTs are employed to measure the current entering and leaving critical components such as transformers, generators, and motors. Differential relays compare the currents from CTs to detect any imbalance, which indicates an internal fault. Upon detecting a fault, the relay issues a trip signal to disconnect the equipment from the system. 4. Transformer protection. CTs are used to monitor the primary and secondary currents of transformers. PTs provide voltage signals for voltage-dependent protections like overvoltage and undervoltage. Buchholz relays, which use CTs, provide protection against internal faults such as arcing or insulation failure by detecting gas accumulation in the transformer oil. 5. Busbar protection. CTs are installed on each phase of a busbar to measure the current flow. 4.8.2. Standard ratios and accuracy class. Answer. Current transformers, CTs, and potential transformers, PTs, are available in various standard ratios and accuracy classes to suit different applications and requirements in power systems. Here are some common standard ratios and accuracy classes for CTs and PTs. Current transformers, CTs. 1. Standard ratios. CTs are typically available in standard ratios ranging from 5A to 5000A on the primary side. Common standard ratios include 100 fifths, 200 fifths, 400 fifths, 800 fifths, and 1200 fifths, where the primary current is divided by 5 to obtain the secondary current. 2. Accuracy classes. CTs are classified into accuracy classes based on their permissible error under rated conditions. The most commonly used accuracy classes for CTs are Class 0.1, plus or minus 0.1% accuracy. Class 0.2, plus or minus 0.2% accuracy. Class 0.5, plus or minus 0.5% accuracy. Class 1, plus or minus 1% accuracy. Class 3, plus or minus 3% accuracy. The accuracy class indicates the maximum deviation from the true value of the primary current at rated conditions. Potential transformers, PTs. 1. Standard ratios. PTs are available in standard ratios typically ranging from 110 volts to 220 kV on the primary side. Common standard ratios include 120 120ths of a volt, 240 120ths of a volt, 480 120ths of a volt, 1200 120ths of a volt, and 2400 120ths of a volt, where the primary voltage is divided to obtain the secondary voltage. 2. Accuracy classes. Similar to CTs, PTs are classified into accuracy classes based on their permissible error under rated conditions. The accuracy classes for PTs are generally similar to those for CTs. Class 0.1, plus or minus 0.1% accuracy. Class 0.2, plus or minus 0.2% accuracy. Class 0.5, plus or minus 0.5% accuracy. Class 1, plus or minus 1% accuracy. Class 3, plus or minus 3% accuracy. It's important to select the appropriate ratio and accuracy class for CTs and PTs based on the specific requirements of the application, including the expected range of currents or voltages, the accuracy needed for metering or protection, and compliance with relevant standards and regulations. Additionally, it's essential to consider factors such as the burden impedance, transient performance, and environmental conditions when specifying CTs and PTs for power system installations. Thanks for watching. Like, comment, subscribe, and share your friends' zone.